Hi everyone, my name is JP Metcalf and I'm a sales engineer at L3 Harris Geospatial. Today I want to present exploring agricultural remote sensing data in ENVI. Here's a quick look at what I'll be covering in this video. I'll talk about different sources of remote sensing and how the spectral, spatial, and temporal resolution might influence your data use decision. I'll then go over the uses of remote sensing imagery in agriculture in the ENVI software, to include synthetic aperture radar, time series analysis, some of our UAV tools, our crop science module, which was made specifically for agriculture, and deep learning module. Then I'll follow up with the croplands data layer estimation use case, which also involves deep learning. So a quick recap on spatial and spectral temporal resolution. Translates to the rate at which you can monitor agricultural fields using imagery depends on the platform. Satellite imagery can have revisit times over a given area ranging from weeks for a single platform or a single satellite, or daily revisit for a large constellation like Planet or Capella Space. With their high orbital altitude, some satellite view angles can cover very large areas, but usually at the expense of ground resolution, like meter-ish size pixels, while others can point and sacrifice the large area for ground resolution, having sub-meter resolution. In aerial, imagery collected on planes or helicopters can get down to a few centimeters of spatial resolution and can use multispectral and hyperspectral and thermal cameras, even LiDAR, although the revisit rate can be very low due to the cost of flying a platform. Imagery from unmanned aerial vehicles will often be on the order of a few centimeter resolution. And multispectral and hyperspectral cameras have been miniaturized to be able to fly on these. And the platform itself can be pretty cheap. From fixed wing or rotorcopter UAVs, they can capture relatively small areas at high enough resolution to get to see individual crops at a frequent revisit rate. So whether your imagery is from satellite, aircraft, or UAV, the remote sensing software suite ENVI can process your imagery and produce a meaningful solution. ENVI uses scientifically proven analytics to deliver expert level results. And for highly specialized tasks, available modules can be called in ENVI to perform processes like atmospheric correction, feature extraction, or even deep learning, to name a few. Everything I'll present from here on out can be processed in ENVI. Analyzing vegetation using remote sensing data requires knowledge of the structure and function of vegetation and its reflectance properties. This knowledge enables you to link vegetative structures and their condition to their reflectance behavior in an ecological system of interest. ENVI has several vegetation-specific indices built in, and the number of indices available can depend on whether the input data is multispectral or hyperspectral, or narrowband or broadband. Nearly all of the tasks shown here can be used in an automated fashion. Speaking of satellites, here's a comparison between an optical and SAR image. The optical image is from Sentinel-2, collected on June 20th, 2018. And in that image, we can clearly see areas of green vegetation and some of those brown, barren fields. With analysis processes, such as producing spectral indices and time series analysis, we're able to find out possible crop types and track growth and change over time. On the right is a TerraSAR X vertical out and vertical receive image, vertical being the polarization. That was collected on June 18th, 2018. And looking between the two, we can notice some differences. If you look at the red circle, even though all these areas show up as some sort of green gradient or that brown gradient with barren in the optical imagery, we have a large difference in the backscatter in the SAR image. Backscatter of SAR is affected greatly by crop type, soil moisture, geometric effects, thus making certain vegetation appear very different from similar green-colored vegetation around it. Areas that are very bright white have a high intensity response, Think of it as the more vegetation, the denser, the larger the leaves, and other factors, the more intensity is going to be scattered back to the satellite. On the opposite side, if it's bare soil, wet soil, it will act as similar to flat surfaces and reflect most of the backscatter away from the satellite, which would be appearing black in the imagery. Here, I have 4 Sentinel-2 images from spanning multiple dates over a field, highlighted in red. Over a 3-month period, these are the only usable Sentinel-2 images due to weather. And you can see the large gap in between the barren field in June, the beginning of growth on August 4th, the greening in late August, and suddenly an empty field in the end of September. We're missing a lot of crucial information about the growth cycle with the limited access of this optical data. So let's see what SAR can give us instead. Now, we're looking at the field we just viewed with our 4 scenes of optical data. Now we're looking at it with a few different SAR sensors. At the beginning of this time series, we see high intensity responses. This is due to plowed soil in preparation of planting the field, as we saw in the June optical image. In the beginning of July, we see a minimum, which is highlighted by the green line. This minimum is related to the sowing stage of the cereal field. After that, the response slowly increases as vegetation grows and the intensity of our backscatter off the canopy and structures increases. In mid-September, we hit a peak in Sentinel-1 data that is caused by the harvesting and upchurning of the soil, as well as leaving some of the vegetation debris on the field. Soon after, with the red line, we see a decrease in the TerraSAR X imagery, which occurs when harvesting is finished and the soil is returned to its normal state. In the SARscape Intensity Time Series tool, SARscape is a module in ENVI, the first output that you get is a multi-band image, where every band is a different date of the SAR imagery. It automatically orders them from earliest to latest image, so you don't have to worry about moving dates around. The image is made up of 3 different dates, shown as red, green, and blue. This allows us to easily view changes within our scene and pinpoint how certain fields are performing during a given time period. Here we have a few fields highlighted in blue, light blue and red, so that we can take a look at the temporal separability of multiple crops. Similar to the optical data, we can use the image made up of multiple dates to track the changes over the entire fields and compare them for analysis. We found 3 fields of interest, and using the time series tool, we can make a comparison of their growth rates over time. Changes in the intensity show us how these fields differ, and this output can be used in tandem with optical data to get an understanding of SAR optical crop interactions for best practices. With this, you can track temporal changes from crop to crop, field to field, or even over an entire scene to see how the crops are growing and how they compare to each other easily. We can also generate a classification of specific field types from this time series. The example on the screen used training data over the entire time series, shown on the left, to find all fields of wheat, shown on the right. There's a little bit of confusion with some of the other crop types, or crop responses, but overall, this quick classification did a great job of finding all other wheat fields, and then could be used to create shapefiles and track their temporal changes for comparison. Moving on to UAV type tools. For assessment of UAV imagery collected in the field, we have Precision Pass. Precision Pass lets pilots quickly determine if a UAV image acquisition meets the required criteria or needs to be collected again. This immediate feedback reduces the risk of failures during the subsequent processing stage, say something like mosaicing or photogrammetry. Precision Pass performs a metadata review to ensure all required metadata are present and are within the specified criteria for the capture, such as positional information like GPS, camera parameters, timestamps, the bit depth of the imagery, and the file format. It also reviews the spacing along and between flight lines to ensure that there is proper overlap and side lap for stitching and analysis purposes. The toolkit can also find gaps between scan lines and compare the collection to a bounding polygon to ensure proper coverage. So let's look at it real quick. In this example, Precision Pass was used to assess the collection of over 1,200 images from a UAV-mounted MicaSense Red Edge camera over a lettuce field in Salinas Valley, California. MicaSense Red Edge camera is a miniature camera that has 5 different spectral wavelengths, 5 different camera sensors with different filters. Based on the metadata, a flight path was generated for review, and the individual image overlays could be viewed along the path. The flight summary tells me that all images were collected with more than 40% forward overlap, and the contrast and the saturation of the collection was good. A little over 200 images were collected without at least 40% side lap due to a UAV launch location, which was just outside the field. So on the left, the UAV traveled to the field, collected, and came back. And that's why we don't have the side lap for those images. At the same time, I received a warning that none of the images were collected with less than 5 centimeter ground sampling distance, or the pixel size. But knowing that it was a MicaSense Red Edge camera, I expected around 8 centimeters GSD, and that's what we received. Once the image collection was assessed with Precision Pass, the imagery can be processed in Pix4D Fields, which is a photogrammetry software designed specifically for agricultural applications. It'll quickly stitch that MicaSense imagery together and produce an orthomosaic. That mosaic produces a 5-band image stack, including the red edge and near-infrared bands, which are useful for looking at vegetation. The images on the right show the false color infrared mosaic with any non-lettuce field areas that were removed. And we also have an NDVI image in the corner. So moving on to ENVI Crop Science module. This platform contains remote sensing analytic tools for precision agriculture. ENVI Crop Science was made to work with agricultural imagery specifically. It's data agnostic, meaning you can pass any type of raster imagery in. All of the tools are available as tasks, and you can generate or create large automated workflows to extract crop information. Once you've defined and counted your crops, the tool can produce all sorts of metrics to get a handle on your field. Crop Science can count individual crops and generate a vector file, including the crop diameter. Here's an aerial image of an orchard where each individual tree has been delineated. Once the crops have been identified, you can use spectral indices to compare each plant to the performance of the whole orchard. Crop Science also has a row and gap finder, and these do exactly what they sound like they do. Crops outside the row can be removed from any subsequent analysis if you want to just evaluate that row. And the gap finder will evaluate crop locations along a grid and determine where gaps are present. An image containing your crop might have adjacent pixels that you might not want in your analysis. In Crop Science, you can delineate your field of interest and then run things like hotspot analysis to find trends in your field, and in your field only. Here we show 3 different indices and use hotspot analysis to determine global spatial statistics within those fields. In developing hotspots, you can pass in 2 indices to determine if areas greatly depart from the mean index. Here are 2 NDVI images where we want to see if any significant change has occurred in the health of the field. The first date's NDVI image show a uniformly high NDVI value for the entire field, with some stress developing in the southern part of the field a few days later. With developing hotspot analysis, we see that the northern area actually had significant positive change, which is very hard to see in the original NDVI image, while the stressed area shows that the negative change was significant. So another module that we have is the ENVI Deep Learning module. It's relatively new to ENVI, and with this module you can train a model to find specific classes based on physical features, beyond just their spectral component. A deep learning workflow basically involves the generation of training labels by delineating groups of pixels that represents your class of interest. Then you would expose that model to the labeled imagery so that it learns how to best find your classes. You can then use the trained model to quickly find your classes in similar images. For example, the presence of weeds can contribute to a decrease in crop yields. To control the weed growth, it would be important to know where they are in relation to your planted crop. Spectrally, crops and nearby weeds can appear almost identical when viewed in true color or even near infrared imagery. Deep learning was found to be useful in identifying crops and weeds by detecting subtle differences in their shapes and patterns. In this example, a UAV collected image was used to train a model to identify the differences between a sugar beet crop and the surrounding weeds, leaving the soil unclassified. The images on the right show the activation values for weeds and sugar beets. Think of the activation images as a probability of those classes belonging to that particular class. Deep learning can be used to find spatial patterns in imagery and provide an ideal solution for locating fields with irregular shapes such as center pivot irrigation. In this example, a deep learning model was trained to find circular irrigation fields found in Sentinel-2 imagery. Notice that there are numerous rectangular fields in the image that remain unclassified. And for our use case, here's a deep learning model applied to planet satellite imagery. These are from July 2017, 2018, 2019, and the same for August. At the time of this project, the U.S. Department of Agriculture did not yet release their 2020 cropland data layer. And what we wanted to do was to estimate what the layer would be for 2020 by creating a deep learning model utilizing the past few years of PlanetScope data. We also pulled the previously published cropland data layers for corn and soybean for 2017, 2018, and 2019. The cropland layers were used as training data so that the model would learn the differences between corn and soybean. So the entire multi-step workflow for the deep learning training and classification task was put into an ENVI model. ENVI models can be run in an automated way. You just you hit run, you give it input, you have tasks. Input is in blue and the tasks are in yellow. And then you can start to aggregate multiple products into one final product. And after running the model, the predicted croplands classification layer for corn and soybeans is generated from an image collected in 2020. If you have any questions about what we went over today, again, my name is JP Metcalf, and I'm at L3 Harris. Here's my email, and here is an email for any ENVI-related questions at the bottom with geospatialinfo@harris.com. And I thank you for your time.